Hello and welcome. In this lesson, we'll explore graphing more rational functions, and our focus will be on graphing rational functions of the form quadratic over quadratic or linear over quadratic. Remember that graphs of rational functions are shaped by their asymptotes, so let's recall one more time how we determine them. For the vertical asymptotes, we follow two very simple steps. Step number 1, determine restrictions, which are the values of x that can make the denominator 0, thus the function undefined. Now, to determine the restrictions, what you want to do is factor the denominator if possible and set each factor equal to 0. If the denominator is non-factorable, use the quadratic formula to find the restrictions. Step number 2, you're ready now to state the vertical asymptotes, which are equations in the form x equals the restriction. So depending on the equation of a rational function, you may find 0, 1 or more restrictions, or we may find 0, 1 or more vertical asymptotes. Horizontal asymptotes stem from the fact that y values will approach a specific value as x approaches either positive or negative infinity. And that won't allow the function to go beyond that value, and that creates a limiting value for y, and that's the asymptote. So approach a specific value, we said. Now, how do we determine them? We have discovered some shortcuts on how to determine the horizontal asymptotes in graphs linear over linear, and we're going to use the same idea in the graphs of function quadratic over quadratic and linear over quadratic. Step number 1, we will have to identify what the highest degree term in the whole function is, and then determine their coefficients. So determine the coefficients, and I say coefficients because we have to find the coefficient of both numerator and denominator of the highest degree term in the function. And I am going to highlight the word function here because it has to be the highest degree term in the whole function. And from here, we can determine the horizontal asymptotes, which are equations in the form y equals the ratio of the coefficients from the numerator and denominator. So let's get started with an example where we can illustrate all of this. So we have y equals 2x squared plus 1x squared, plus 2x plus 1 divided by 5x squared minus 3x minus 2. So to find the vertical asymptote, I will need to factor the denominator, which I will right now. And it seems that this is factorable because I can find two numbers that multiply to 5 times negative 2, negative 10, and add to negative 3. So I will start with 5x and x, and we'll say that here we're going to need a negative 1, here a positive 2. So that would be 5x squared minus 5x plus 2x will give negative 3x, and the product is negative 2. I won't do anything to the numerator for now, so that would be x squared plus 2x plus 1. So from here, I can state the restriction and say that x has to be different than negative 2 over 5 and different than 1. So therefore, the vertical asymptote, I'm going to write it down here better, are 2 as a matter of fact, and their equations are x equals negative 2 over 5 and x equals 1. So here go the vertical asymptotes. And let's take a look at the horizontal asymptotes. So I have to examine the equation and check and see what the highest degree term is here. So the highest degree I see in the numerator is 2. The highest degree in the denominator is 2. So that means that the highest degree term is degree term 2. So the highest degree is 2. So the next thing you want to do is identify the coefficients of the term of highest degree from both numerator and denominator. So here coefficient is 1 and here coefficient is 5. So therefore, we'll say that the horizontal asymptote is the equation y equals 1 over 5. Now, I'm going to extend the idea or the examples in here to some more in here so that we can find the horizontal asymptotes easily. So here we go. I'm going to give another example, which is not in the handout. So we have y equals negative 3x squared plus 4 over 2x squared plus x minus 1. So again, I check and see what the highest degree is in the whole function, which is 2. The ratio of the leading coefficient of the numerator is negative 3, and this is 2. So horizontal asymptote is y equals negative 3 over 2. Let's take a look at another one. So y equals x minus 2x squared minus 4 over 4x squared plus 3x. So the highest degree term in this function will be power of 2. It is present in both numerator and denominator. The coefficient of x squared in the numerator is negative 2 and the denominator is 4. That tells me that the horizontal asymptote is y equals negative 2 over 4, and even better, y equals negative 1 over 2. Let's take a look at another example. We have y equals 5x plus 3 over 2x squared minus 1. The highest degree term in the function is 2. When you look at the numerator, though, we are missing the x squared. So in this case, what we want to do is give x squared a coefficient of 0. And now we haven't changed the expression, right? We just made it look different, and we made the coefficient of the highest degree term in the function visible. So the coefficient of the denominator, in the denominator, the coefficient of highest degree would be 2. So therefore, the horizontal asymptote will be the equation y equals 0 over 2, or simply 0. Now the same idea applies to, I'll give you one more example. So we have negative 4x plus 3 over 2 minus x minus 7 x to the power of 2. So the highest power in the function is 2. The denominator has a power of 2, obviously, but numerator doesn't. So what we do is we add an x to the power of 2 to the numerator with a coefficient of 0. So now we have 0 over negative 7. So y equals 0 over negative 7, or horizontal asymptote is y equals 0. So as you can see, whenever we are missing an x squared term, so whenever we have a linear in the numerator, in other words, and a quadratic in the denominator, then the horizontal asymptote will always end up being y equals 0, something that is worth noting and remembering. So let's take a look at some more examples. Now, this is some more explanation about how we determine the asymptotes. There are two types of horizontal asymptotes in rational functions. Either y equals 0 or y equals a real number. So this is a summary of what we just explained. So when do horizontal asymptotes y equals 0 happen? It happens when the degree of the numerator is less than the degree of the denominator. What does that mean? It means that if a rational function is in the form y equals a linear over quadratic, or even y equals a linear over cubic actually, or any degree higher than 1, or when the rational function is in the form quadratic over cubic, then the horizontal asymptote will be at y equals 0. Now, the horizontal asymptote will be y equals some constant real number, different than 0, if the degree of the numerator would be equal to the degree of the denominator. For example, if we have y equals linear over linear, or y equals a quadratic over quadratic, beautiful writing here, sorry about this. Easy to get excited when you talk about math. So y equals cubic over cubic, or, and you can continue on forever. So why does this happen? Let's take a look at the examples, and this will become clearer, we hope. So let's identify the horizontal asymptotes, just the horizontal asymptotes in the following examples. Now, f of x equals 5x squared plus 1 over 3 minus 2x squared. So the highest degree in this function will be degree 2. It is present in both numerator and denominator, so we have quadratic over quadratic in here. So that means that the horizontal asymptote would be y equals the ratios of the quadratic terms, which are 5 and negative 2 for the denominator. And you're done. Next, we have the highest degree term in the function, 2. And the power 2 term is present in both numerator and denominator. That tells us that the horizontal asymptote will be y equals 2. Next, the highest degree term in the numerator is 1, denominator 2, which means that the highest degree term in this function will be 2, which means again that the numerator will be, or we can describe the highest or the power 2 term as 0x squared. And then we'll check with the coefficients. So here we have 0, here we have 2. That means that the horizontal asymptote is y equals 0 over 2 or y equals 0. Remember that you can either remember to state the asymptote as y equals 0 by comparing the degrees, linear over quadratic, or you can remember the rule that we need to check for the highest degree term of the function. And if we're missing it, then we give it a coefficient 0, and that will give us the asymptote. Now, take a look at this very interesting function. So what we have in here, probably it's not that visible, but this is a negative 4, by the way. I'll make it black as well. Why not? So we have negative 4 over x squared plus 1. So the highest degree term here is 2. An x squared is missing from the numerator. So we're going to say that we have plus 0x to the power of 2. So we're going to say now that the coefficient of x squared in the numerator is 0 and the denominator is simply 1. So the horizontal asymptote will be at y equals 0 over 1 or 0. Again, you can remember that the degree of the numerator is lower, and that's what makes the horizontal asymptote y equals 0. Or you can also explain it or add a 0x squared in here to match the degree of the denominator. Next, you probably spotted it right away that the horizontal asymptote here will be just 3 over 4. So we'll write here horizontal asymptote is y equals 3 over 4. Next, we have the highest degree, 2. So coefficients, 7 for numerator, negative 2 for denominator. Horizontal asymptote will be at y equals 7 over negative 2. So this is how we find the asymptotes, and in the next part we will discuss how to graph a function. Thank you for listening and choosing to learn from me. Bye for now.